9.2 Taylor Series. Take a minute to read the essential questions for this lesson. We're going to be working with power series, and a power series means you're working with powers, polynomials. And here's just a brief review about polynomials and the degree of the polynomial and its name. We're going to take a look at trying to represent the sign of x as a polynomial. And we're going to call this a Taylor series. Now, we're not going to start it right away. Let's first begin with this task at hand. Let's just work with any function in general. So I'm going to work with, I want f of x. F of x is a polynomial. And we're going to evaluate at f of a plus x. I'm going to assume that f of a plus x can be written as a polynomial and so on. And in summation notation, it would look like this. Okay, so it's a little problematic because this is infinite and we really don't know these constants that are in front of each term. So let's go ahead and put these requirements. First, let's put this requirement. Let's set x equal to 0. And when we do that, I'm going to put a 0 in for every x. This will be f of a equals c naught plus c sub 1 times 0 plus c sub 2, 0 to the second, and so on. What's happening is all these terms are going to be 0. So I can conclude that f of a is equal to c sub 0. So I already have a representation for the constant here. Second, I am going to take the derivative of the function, which means I'm going to take term by term derivatives here. So this will be c sub 1 plus 2c sub 2x plus 3c sub 3 x squared plus 4c sub 4 x to the third plus 5c sub 5 x to the fourth, and so on. Again, I'm going to set x equal to 0. This means that f prime of a, remember x is equal to 0, all of these terms here will be 0 and I'll only have c sub 1. So now I have a representation for this constant here. My third step, I am now going to take the second derivative, which means I'm going to do term by term derivatives. This will be 2c sub 2 plus 2 times 3 c sub 3x plus 3 times 4 c sub 4 x squared plus 4 times 5 c sub 5 x to the third. Alright, I am going to again set x equal to 0, which means that f double prime of a is equal to 2 c sub 2, which implies that the second derivative of a divided by 2 will be c sub 2. So I have found a representation for c sub 2. This next screen will show you how I find the representation for c sub 3 and for for the nth power here of a plus x. And I will end up getting c sub n to be equal to this. So I have shown you a way to take this function and find a way to represent it in terms of derivatives and factorials. If you go to your notes, you'll see the discussion written in type form here as I described it to you. And here is nicely typed conclusion that I showed in the previous screen. All right, let's go ahead and practice once more this process. We have done this before, the natural log of 1 plus x. We've written it when we were studying the geometric series. Let's go ahead and use the same process that we just did a few minutes ago. All right, so we know that the natural log of, let me go ahead and change this, natural log of 1 plus x will be equal to a sub naught. It's actually approximately equal to, not exactly, but we're gonna go ahead and put an equal sign. It'll make our life a little easier. Okay, so I'm going to again set x equal to 0. So this will be the natural log of 1 is equal to a sub naught. And so I know this first term is going to be 0. So that implies 0 is equal to a sub naught. Now I'm going to take the derivative of 1 plus x. I'm sorry, the derivative of natural log of 1 plus x, which is equal to 1 over 1 plus x, and that'll be equal to the derivative on the other side, which is a sub 1 plus 2a sub 2 x plus 3a sub 3 x squared plus 4a sub 4 x to the third. We're going to set x equal to 0, so this will be 1 is equal to a sub 1. We're going to continue this process on the next screen, and I'm going to find my a sub 2, my a sub 3, and my a sub 4. And notice these are the values that go right here, and it matches this answer right here that I arrived at when I was doing the geometric series. Okay, so what we've constructed is what we call a Taylor polynomial. It was finite, it ended, and it was the beginning of the power series we discovered in section 9.1. Now, the series is called Taylor series, generated by this function natural log of 1 plus x at x equal to 0. Now these are all polynomial approximations that are near 0. All right, series for sine of x and cosine of x. Let's construct the 7th order Taylor polynomial. So we're going to go to the 7th power when we do this. All right, let's go ahead and we are going to do it for sine of x, which is what we started off with. Okay, sine of x is going to be equal to a sub naught plus a sub 1 x plus a sub 2 x squared plus a sub 3 x to the third plus a sub 4 x to the fourth, and we're going to keep on going till we get to a to the 7th x to the 7th. All right, so we know we're going to set x equal to 0, and we're going to have sine of 0 equals a sub naught. And well, sine of 0 is 0, so 0 is equal to a sub naught. Okay, now we're going to take the derivative of sine of x, which means that's going to be cosine of x, and we're going to take the derivatives of each of these. So that's going to be a sub 1 plus 2a sub 2x plus 3a sub 0 x squared plus 4a sub 4 x to the third, and we're going to continue this pattern, 7a to the 7th x to the 6th. We're going to let x equal to 0, so this will now be, when I let this be 0, that's going to be a 1 equals a sub 1. So now I have a representation for a sub 1. Now let me go ahead and show you, kind of, since I knew I was going to do it over and over again, I ended up taking all the derivatives, and I know that as you continue to take derivatives, it's creating this factorial because the exponent keeps coming down and coming down and coming down. So I know that when I evaluate this, I have this factorial, and then a sub naught or 1 or 2, and then I went ahead and I just solved. So I found all these values. A lot of them were 0, and so that's why when the a sub naught term was 0, that's why we didn't see it, and over here it ended up being 0. So we didn't get a quadratic here. We didn't get a power of 2, power of 4, power of 6, because every time you take an even derivative, you ended up getting a sign, and the sign of 0 is going to be 0. So that's the representation for, this is what we call seventh order Taylor polynomial. All right, now what does this show us? Well, here was the first order, third order, fifth order, and as you see, the polynomial is getting better and better at approximating the sine function. Maclaurin and Taylor series. Okay, a Maclaurin series is when the function is centered at 0, so it's evaluated at 0. And that's called a Maclaurin series. Now, when a function is centered at x equal to a, it'll look something like this. Instead of an x to a power, it'll be x minus a. And that's called a Taylor series because it's not at 0. We can also call a Taylor series when it's centered at 0, but on the AP test, they might say Maclaurin, and Maclaurin means it's absolutely at 0. Okay, let's take a look at finding a Taylor series at x equal to 2, which means our center is at 2. We're going to have these polynomials here that are a little bit more complicated. Now, we're going to find the derivative of e to the x each time, and each time we take it, it's itself. So each one of these derivatives is the same thing, evaluated at 2. It's e to the second. So all these coefficients are the same. I mean, the derivatives are the same, but we still have to have the factorials here. And so here is the representation for e to the x centered at x equal to 2. Now let me go ahead and push the screen up a little bit so that you can see the more and more terms we have, the more and more it looks like the natural, e to the x right here. And again, notice that the center here is at 2. So as it goes farther out from 2, the polynomial looks like it matches the function more and more. Now here are all the Maclaurin series for very important functions, function representations. This is in your book, and it would be to your advantage to memorize all of this. You'll get through things a lot faster if you do. And that's the end of the screencast.